Sorry, wait a moment. We have some problem with Okay.
我不知道这个，这个是不是？或者我们把这个，不是它这个 share 的话是怎么弄的呀？哦 ，sorry， 哦，我先。
Inform you.
Right, yeah.
So how to maybe we need the full screen. View full screen, enter full screen, enter full screen, and then let me try.
不是，你要插这个，你要插个 USB
啊 ，I see.
USB。哦，你这里不能接 USB 是吧？那你就直接。我。没有。等一下，要把这个打开。不行是吧？不行就手。
Oh, it's okay, it's okay, it's okay.
OK。这个怎么？
你这个不用动啊，对就可以。We need to move this to.
应该早点准备，忘了跟你说这个事情。
OK。你需要，
我就对着这个说就可以。
你问问那个 Prof. Kong 他能听吗？
他可能现在。Hello, Professor Kong, are you here? I can't see you, but can you hear me?
I guess we have opened the.
OK。你在那说话，我在那去测试。
Hello, Professor Kong, can you hear us? Hello. 哦，他是不是听不到我们说话
？Hello, everyone. I
think it's okay now. Yeah.
Hello,
okay, good. Yeah.
Can you hear us? Hello, Shen, can you hear us?
Okay, maybe I just okay. It's time now, so maybe I just do the introduction. So today we are going to have two talks. Both are from the Institute for Basic Science. The first talk is given by Dr. Feng Shao. He will talk about the bigness of tangent bundles of projective manifolds. Okay, you may start. Okay, thank you.
Thank you. Thank you for the invitation. Today, I will talk about the bigness of tangent bundle or projective manifolds. Okay, today, I thought will.
I guess you may be a little bit louder. A bit louder.
Okay. Today my talk will be divided into 4 parts. And so the first part is the motivation and the introduction. The second is basic definitions and the properties. And the third part, I will give the idea of our main series. Our main series is about the classification problem. And the last part, I will introduce some remaining problems. Okay, first, let me introduce our motivations. Our stories begin from the famous Shao conjecture proved by Murray in 1979. It states that if X is a complex projective manifold, then its tangent bundle is ample if and only if X is isomorphic to a project space. So it's natural to consider a problem that can we classify the project manifold whose tangent bundle have weak positivities and ampleness. So in 2015, Xiao asked the following question: can we classify a project manifold whose tangent bundles are big? And he also asked that if X is a final manifold with left tangent bundle, is it true that the tangent bundle is big? And these 2 questions, in fact, has a deeper relation with the famous Kaplan-Pinel conjecture. The conjecture states that if X is a project final manifold with left tangent bundle, then X must be rational homogeneous. So in Xiao's question, if we can classify the final project manifold whose tangent bundle is big, and the second question, if the second question has a positive answer, then maybe we can prove the Kaplan-Pinel conjecture. But now it seems that it is impossible. Maybe it is impossible to give a classification or project manifold. Maybe even in the final case, we cannot classify the final project manifold whose tangent bundle are big. But for some special kind of project manifold, we can classify the project manifold whose tangent bundle are big. Okay. Next, we see some examples of project variety with big tangent bundles. The first one is project space. We know that its tangent bundle is ample, so in particular, its tangent bundle is big. The next example is the rational homogeneous space. Its bigness of its tangent bundle is from the generic finiteness of the project spring map. And in fact, okay, how to say? We know that the project spring map is a generic finite morphism, and the generic finite an ample line bundle, the product of ample line bundle under a generic finite morphism is big. So by using the project spring map, we can show the bigness of tangent bundle or rational homogeneous space. And the third example is the smooth projective product varieties proved by Xiao in 2015. And the fourth example is the non-homogeneous project symmetric varieties proved by Jie Liu in this year. And he also proved that the non-homogeneous smooth project or spherical varieties also have big tangent bundles. And the last example is the development for the degree 5. Next, we see some results about the bigness of tangent. See some classification results about the bigness of tangent bundles. The first theorem is for the dipole surface. We let X be a smooth dipole surface or degree D. Then its tangent bundle is big if and only if its degree is at least 5. And a similar result holds for the dipole threefold. And the last theorem is about the classification result for the smooth hypersurface in projective space. And we show that if X is a smooth hypersurface or degree D in a projective space, then its tangent bundle is big if and only if its degree D is at most 2. And today I will mainly introduce the proof or these 3 theorem. Okay.
So have you introduced the definition of smooth diapascal threefold? What's the difference between diapascal threefold and panel threefold?
The definition is following a dipole manifold. A smooth dipole manifold is defined if its anti-kinetic divisor can be written as the dimension x minus 1 multiple h, where h is the ample divisor.
It is not dimension x plus 1, otherwise it's projective space.
Yes. And later I will give a classification or the dipole manifold. It is a very classical result, classical classification. Okay. Next, we see another some classification results. The first result is proved by Hervey and Jieliu last year. They shows that if X is a final threefold of pickup number 1, then its tangent bundle is big, and if and then only if it's high, the top intersection number of minus kx is at least 40. That is X is a project space, 3-dimensional project space, and Q3 or the parallel 3 for the degree 5. And also in this year, 3 Korean mathematicians shows that if X is a final 3 for the pickup number 2, then its tangent bundle is big if and only if the top intersection number or minus kx is at least 34. And they also conject that in the final threefold case, there is the constant C0 depend only on the pickup number or x, such that its tangent bundle is big if only if it's the top intersection number or minus ks is at least C0. I guess that maybe the conjecture can be extended to the high dimensional case. If we maybe in the high dimensional case, the constant 0 maybe depends on the pickup number or x and the dimension of x. But now it is only a conjecture. And the last theorem also proved in this year is about classification result for project bundle over a curve. It states that will let C be a smooth project curve and E a wave bundle on C. Then the project bundle X has a big tangent bundle if and only if E is unstable or the base curve is P1. Okay. Is there any questions?
Your C here can be arbitrary genus.
Yes, arbitrary genus. Okay. And let's
And eventually it has to be P1.
Yes.
Okay.
Or it has to be P1 or E is unstable.
So if the tangent bundle is big, can you say that it must be rationally connected?
Not only unit rule. Yes. Maybe not original connectivity.
But in this case, it must be rationally connected.
Yeah. If the genus or C is at least one, then yeah, maybe X is no original connected. Okay, let's continue. Now let's record some basic definitions and properties. First is the definition of big divisor. Maybe you are quite familiar with this definition. We let X be a smooth projective variety and D is a divisor on X. We see that D is big if the target dimension of D is equal to the dimension of X. And we see that D is a pseudo effect of D is a limit or big R divisors. And we can extend the bigness or pseudo effect or divisor to the valid bundle case. And we let E be a valid bundle on X. We see that E is big if the tautological line bundle is big on the quadratic projective bundle. Okay, and then for big valid bundles, there are many equivalent descriptions. Let theta be the first chain class of the tautological line bundle, and we have the following equivalent statements. First is E is big, and if only if the symmetric product or E in fact has many sections. The third is the symmetric product or E just the dual or ample line bundle has sections. The last is that exists an ample Q divisor H such that this divisor is effective. So from these equivalent statements, if we want to know whether bundle is big or not, you only need to calculate the comerge group of the symmetric product or E, or the comerge group of the twisted symmetric product or E. But usually it is very hard to calculate the comerge group. Okay, from the equivalent description of the big valid bundle, we have the following observation. If X is a smooth projective variety, then the bigness of the tangent bundle implies the unirolness of X. And the implication is by Miaukas's criterion of unirolness. We see that if the comerge group H0 symmetric product of the tangent bundle just L minus 1 is not 0, then we have the following suggestion. And this suggestion shows that the cotangent bundle of X is not generically semi-positive. So by Miaukas's criterion or unirolness, we see that X is unirolled. And it is an easy observation. And next, we try to show our next. I give the idea or our main results. And our main result is to classify some special kinds of projective manifold with big tangent bundles. The first is dipole surface, and the second is dipole threefold. The last one is a smooth hypersurface in a project space. First, I introduce the main tools when we prove our main theory. Our main tool is called projective VMRT. First, let's record the definition of VMRT. We let X be a uniruled projective manifold of dimension n, equipped with a domain family or original curve K, and for general point X in X, there exists a rational map, tau X. We call it is a tangent map. Here, Kx is the family or rational curves in K. Kx is a normalization of the family or rational curves in K that passing through the given point X. And the tangent map sends the general element of Kx to its tangent direction. And we call the image of the tangent map the variety of minimal rational tangents. And we use VMRT for short and denoted by Cx. And next, we can give the definition of total dual VMRT. We let Cx track be the projective variety of Cx. Then the series closure of the Cx track. The union the series closure of the union of the Cx track, and we call it the total dual VMRT, and it is contained in the project bundle of the tangent project tangent bundle of X. Now here okay, we use C track to denote the total dual VMRT. Okay. Next we give another equivalent definition of total dual VMRT. Maybe this definition is more geometric. We first will suppose that X is not a project space, and we let C be a standard rational curve in K. Here K is also a dominating family or rational or minimal rational curves, and the general element, we know that the general element in K is a standard rational curve. Yeah, we let F be the normalization, and then we define the minimum section to be a minimum section or the project tangent bundle over C is a section correspond to the quotient, C quotient. So here we need to assume that X is not a project space. Here, you know that if X is a project space, we don't have C quotient. So if X is not a project space, we have the Z quotient, the probable tangent bundle to the trivial bundle, and we denote the minimum section by C bar, and the total dual VMRT C chart can be also defined by the following: the third closure or C bar, and it is also containing the project tangent bundle. And it is the equivalent definition of total dual VMRT. In fact, okay, and from the first definition, you can see that if Cx the VMRT Cx is not due defect, then Cx track is a hypersurface. So if for general points, the VMRT Cx is not due defect, the total dual VMRT C track is a divisor in the project tangent space. Okay. Next, we see an important theorem. This theorem is why it is, will tell us why it is important to study the total dual VMRT. We let X be a final manifold or pure number one equipped with a dominating family or minimal region curves. Then we let H be a ample generator of the pure group or X. And then the lambda be the topological divisor of the project tangent bundle. And then we assume that the VMRT at general points is not due defect. And this assumption will imply that the total dual VMRT in fact is a divisor in the project tangent space, project tangent bundle. So there, under the assumption, there exists integral A and B. That is, the total dual VMRT can be written as A lambda minus B pi star H. And we can show that its tangent bundle is big if and only if B is positive, is a positive interval. So under our assumption, if you
why here you use numerical equivalency? Because everything is rational, but your final manifold, so Q is true, so it is always Q linear equivalency, right?
Yes.
And in general, is your C check is it is effective either, but
Yeah.
it may not be reducible. Is it possible to be reduced? Has some multiplicity or not? You don't consider multiplicity here.
Yes.
When this C check is divisor in
If the V multi at general point is not due defect, that means the projective variety of CX is a hypersurface. So in this case, the total V multi is a divisor.
Is there any example for this technical condition to satisfy?
In fact, in many examples, the V multi CX is not due defect.
There are many.
There are many examples. In fact, for there are only a few examples, such as VMRT, the general point is due defect. Only a few examples. So under assumption, if we want to know the tangent bundle is big or not, you only need to calculate the total VMRT. But usually, it is also very hard to calculate the number, the integral A and B. Okay, but if X has a Corning bundle structure, then we can calculate the total VMRT. It can be formulated as the following: as C. Here we X is a project manifold with a Corning bundle structure, and here in this case, the total VMRT C check can be written as theta plus pi star relative canonical divisor. And by using this formula, we can calculate the total VMRT. First is for divisor surface of degree 5, and divisor surface of degree 4, divisor surface of degree 3. Also, divisor surface in fact has Corning bundle structures. By using the Corning bundle structure, we can calculate the total VMRT very easily. And okay.
What's the meaning of your set? Why you have a sum of two?
And because we have different dominating family or regional curves.
You have different separations.
Yes, different. Because we have different Corning bundle structure. And the dominating family or minimum regional curves, this family is given by the Corning bundle structure. So if we have different Corning bundle structure, then we have different total due VMRT. So from the first calculation, you can see that the theta it is a topological divisor of the project bundle, and from in the degree 5 case, you can see that the tangent bundle is big from the calculation. And from the second, in the degree 4 case, you can see that tangent bundle is effective. So in particular, it's still effective. And by studying the and by using some geometrical method, you can also show that in the degree 4 case, tangent bundle is not big. Yeah, maybe we need more discussing. Okay. And for developed service case, for degree 3 case, by using the formula, you can see that tangent bond in fact is not big. In fact, for developed degree 3 case, tangent bond is not even not effective. Okay. So we can now prove the first main theory. Our first main theory is about the characterization of the pedal or surface with big tangent bond. Then its tangent bond is big if only if its degree is at least 5. First, first step is the following observation. If the developed surface or degree D is at least 6, then it must be a toric variety. So we know that for toric varieties, their tangent bonds are big. So the degree D is at least 6, then we know that tangent bonds are big. And step 2, I explained just now that for developed surface of degree 5, tangent bonds are big. And for developed surface of degree 4, we know that tangent bond is not big, but its tangent bond in fact is pseudo-effective. And for developed surface of degree 3, we know that its tangent bond is not pseudo-effective. So in particular, its tangent bond is not big. Now last step is about the following lemma. We let mu be a bidirectional morphism between projective manifold. If the tangent bundle of X is not pseudo-effective, then the tangent bundle of T prime is also pseudo-effective. And we know that for the pedals surface or degree 1 and degree 2, they are blowing up the pedals surface or degree 3. So by using this lemma, you can show that for developed surface or degree 1 and degree 2, their tangent bonds are not pseudo-effective. So now we can show our first main theory. Next, we see and we record the classification of pedal manifolds or dimension at least 3. Maybe maybe you are quite familiar with the classification. And for degree 1, there are and here we let X be an n-dimensional divisor, and for the degree D, and if D is 1, then X must be is a hypersurface or degree 6 in the weighted project space, and if D is equal to 2, then X is a hypersurface degree 4 in a weighted project space, and if D is equal to 3, then to the cubic hypersurface, and for D is equal to 4, then X is a complete intersection or 2 hypercortex in T in a project space. And for degree equal to 5, they are in fact a linear section or the Grassmann. And for degree at least 6, then in fact from the characterization you can see that X must be a toric variety or rational homogeneous. So if the degree of X is at least 6, their tangent bundles must be big. Okay, next we begin to prove the main theory. From the characterization you can see that I explained before that the degree or X is at least 6, then their tangent bundles are big. So we only need to consider the case that degree D is at most 5. So in this case, the Picard number or X is equal to 1. So So in this case, we only need to calculate the total durability. Okay. And yeah, we let x be a divisor 3 for the peak number 1 and its degree d is at least 5. We let k be a dominating family or minimal curves, and q be the normalization of the universal family, and we denote by e be the evaluation morphism. And in our case, the evaluation morphism is a generic finite morphism, and we can define degree of the evaluation morphism by k, and also divide the sigma by r. R is the number of rational curves L in case they contained in D. Then we can calculate the total durability. Total durability can be formulated as following. It is in fact equal to k theta plus pi star, r divided by e minus k 1 times h. Now from the formula we can show whether time bundle or x is big or not. Okay. Yeah, from this lemma and by calculation we can show our second main series. Okay. Is there any questions? Let's continue. Okay, our last theorem is about the classification results of the smooth hypersurface or degree D in a project space. And our classification result, in fact, is based on the following vanishing result. In fact, the symmetric here we let x be a smooth hypersurface of degree D, and Gx is tangent bundle. Then we have the following vanishing results. So by the vanishing result, we can see that its tangent bundle is big if and only if its degree D is at least 2. So next we give an idea to show how we can show the vanishing result.
Sorry, you also there the bracket you mean the pseudo effective. So what's you mean TX is big or pseudo effective if only D is lower than 2?
In fact, from the vanishing result, you can see that if the degree of x is at least 4, then its tangent bundle is not pseudo effective. But in the degree 3 case, from the vanishing result, you cannot see that its tangent bundle, its tangent bundle is not pseudo effective. Here in the degree 3 case, we need more discussion.
But you mentioned this TX is big if and only D is no more than 2. But
yes.
What about the pseudo effective case? So the bracket means
the tangent bundle is pseudo effective if and only if its degree D is at most 2.
you mean big and pseudo effective are the same?
Yeah, it's that same.
So the boundary because it's a hypersurface. So you for example, if D is equal to 2, then TX is bigger.
Bigger. Yeah.
I see.
Because hyperquadratic is a regional homogeneous space. So its time bundle is big. But today we mainly focus on the bigness. Yeah. We are not focused on the pseudo effectiveness.
So the vanishing is for any R.
Sorry.
The vanishing theorem is for any R, sim R.
Yes, for any positive integer R.
Okay.
Okay. Next we give a proof or the vanishing result, and our tool is called precision. The definition of precision is very easy. The precision, in fact, is a composition of two Schur functions. And the Schur function, in fact, is given by our partition. Okay. Here, there is a very classical result, classical proposition, improved by Littlewood in 1940. It states that the composition of two Schur functions is can be decomposed as the direct can be written as a direct sum of Schur functions. And here the integer a mu omega nu is a non-negative intervals are non-negative intervals, and it is a very classical result. And the precision problem is to determine the non-negative interval, the non-negative intervals. And in fact, in general, it is very hard. It is very hard to determine the non-negative intervals. But only up to now, we only need to only know some special examples. Okay. Here. So why we need to consider the precision? Because we have the following observation that the symmetrical product of the tangent bundle Tx can be written as, in fact, the tangent bundle Tx can be written as the wedge product of cotangent bundle tensor omega x minus 1. So the symmetrical product of the tangent bundle can be written as the following. Here we have the composition of the symmetrical product and the wedge product. Here is now we can see here is a precision. So we need to consider the precision, and we prove the lemma that here we let K be a positive integer and B is a compressed vector space or dimension and at least 2. And for any positive integer R, we have a GLD module isomorphism. And here, in fact, V can be replaced by a vector bundle or rank at least 2. And by using the lemma, we can see that the symmetric product of the tangent bundle can be written as this Schur function acting on the cotangent bundle tensor the anti-canonical divisor. Okay. And from the observation, we can calculate the common group. Here, there is a theorem proved by Brickman and Rockowitz. They calculate the common group of Schur functors acting on cotangent bundle twist OXP. They show that under some assumptions on the Schur functor and the coming intersection and the P, on some assumptions, the common group vanishes. So by using their vanishing results, we can show our vanishing result. Okay, so here is the main idea is to using the precision, and by using the observation, we calculate the we can transfer the calculation of symmetric product tangent bundle to the to calculate the a true functor acting on coded bundle is the independent divisor. Okay. And the next, I will introduce some remaining programs. The first program is about the bigness of tangent bundle or smooth comping intersections in a project space. And we let X be a smooth comping intersection or dimension at least 2 in a project space. Fx is not a project space or hyperchoric. Is it right that tangent bundle is not big? And the C question, in fact, has a positive answer if dimension of X is at least is at most 4. So in a small dimension case, in fact, C question has a positive answer. But in high dimensional case, I guess C question has a positive answer, but I don't know how to prove. So from the first question, it's natural to ask the second question. Yeah, if X is a smooth project variety with small codimension, and X is a non-project space or a choric, it choose as tangent bundle is not big. So by using Hartshorne conjecture if X has a small codimension, then X must be a comping intersection. So from the first question, it's natural to ask the second question. So from the second question, yes, the bigness of tangent bundle maybe has a relation with the codimension or X in a project space. Yeah. Okay. Next, we see the third question. The third question is about work conditions on a smooth complex variety X beyond the unirolness are imposed by the bigness of tangent bundle. We know that the bigness of tangent bundle implies the unirows, but we don't know other properties of X with big tangent bundles. And then in the Picard number 1 case, are there any relations between the bigness of tangent bundle and the length of X? And in fact, for unirode variety, we have the notation called length. It is a number of original curves that connect to the 2 journal points or X. In some special project variety, I can show that the length of X has in fact has some relation with the bigness of the tangent bundle. Yeah, I show that for irreducible Hermitian symmetric space or compact type, their bigness in fact has a relation with the length of X. But I don't know, whether other project varieties has a relation with the length of X. And the last is a conjecture about the bigness of tangent bundle of the Pellet manifold. And we conjecture that if X is a project manifold of degree D, then its tangent bundle is big if only if its degree D is at least 5. And before we have shown that for Tiberizo manifold, Tiberizo surface, Tiberizo threefold, and the conjecture is true, but we don't know the high dimensional case. Okay. Okay. Thank you.
Okay. Thank you. Thank you very much for the nice talk. Any question? Yeah.
Any question?
Do you have any question? So can you give, do you have any related results on the relative version of this kind of, for example, the tangent bundle being the relative big? For example, you're given a variety of a variety over some. I mean, given a family of varieties, X over Y, such that the general fiber is there has a manifold. Then you can use the total space. The amount of the total space is also big over the base variety. Have you ever seen this kind of result?
No. You mean every fiber is depends on
Fiber is there puzzle, but the
Fiber
base
is-
can be arbitrary. Yeah.
maybe I remember that the base is P1 and the general fiber is depends on manifold. So maybe it's the general fiber is depends on manifold or degree at least 4. Then the total space, the tangent bundle or total space is not big.
I have another question. Since you mainly focused on the Bell puzzle surface, I mean final surface. Okay.
Yes.
So is it true? Have you known that and is it classified for all the rational surface which tangent bundle are big? Because you only focus on the Bell
Yes. For
because you mentioned that toric varieties are true, right?
yes.
Tangent bundles are big, but there are some non-toric, non-final, something like phenotype, but sometimes may not be phenotype, something like. It's not so. Surface case is still not fully classified.
Yes, in the server case, if it is not final, the configuration problem is very difficult. And I remember that some mathematicians give a partial classification of the surface with pseudo-effective tangent bundle. You only give a partial classification.
So what you mainly use is the birational relationship, because for example, if you have a birational morphism and if the target is not, I mean, if the image is does not have big tangent bundle, and the pre-image also does not have
Yes.
tangent bundle. Right?
Yes.
So this is only what we can use for the general case.
Yes.
But maybe surface case is still okay.
Suppose you have already drawn the minimal surface, right? Because the minimal smooth surface as just classified by Johnson.
Can you speak up? We cannot hear you. Yeah.
You go here.
Sorry.
The next time you use another picture.
Sorry, Prof. Can you hear me? Sorry. Can you hear me now?
Still.
Sorry, Prof.
The voice is too small. Yeah. Okay.
Yeah, as Justin mentioned, the minimal raw surface case has already been classified. So if we start from the minimum model of the smooth surface, the tangent bundle being big implies that it should be the vector bundle should be unstable. I mean the non-rational case. So for the non-rational case, we may start from the last step to see how many blowups of that we can get. The first get the non-bigness of the tangent bundle.
But the blowing up may be destroyed. Maybe after the one blowing up, the tangent bundle maybe not
change.
Yeah. The blowing up will destroy the bigness.
Okay. Any other question? No, that's not. Okay. Thank you. Now four. 4 p.m. 4 然后你用那个电脑连一下，这样子等一会儿可以有问题要去再说。电脑连上，然后因为我一先连一下这个电脑，这样好多问题，要不然它跑到前面去。哦。建议你不要。 我建议你用 Adobe 的那个，不要用 Preview
的更好一点。
哦，不是，
你这以后都要设置。腾讯以后你万一国内什么腾讯会议的时候，你这个还是得给权限，要不然你突然弄一下就很麻烦。
所以我把这个关掉。
可以关掉。Stop sharing。Stop share。
然后我再 share 我的那个。
你自己弄的。所以你说这个曲线的你只能说它不是这个往前走的线，不是这个，但是你不知道它看见包的什么关系。它那个定义它所有的关系都是。它是给看见包的关系，你有白日梦。哦，对呀，就找到了那个。就是你给出 x 撇到 x 的白日梦，你怎么给出它相应的方口之间的这个 p x 之间它的一个比例？哦，这个意思的话，就要说什么的口本？它不是PX 是 product projective。你所有都在 X 上做是吧？对，都是在 X 上做。然后它 O1 跟它的那个之间的关系是有点之间。你不是要算，你最终还是要算 O， 就是 TAK 的包括的那个 O1 了，对不对？它们 O1 是什么关系？你跟那个 selection 放进去。但是他们只给出了一个部分。就像 P 不让所任何一个点，它看一个不让点，P 不让2个点的时候，最后不让 P 不让3个点的时候，P 不让3个点，但这3个点现在3个点其实比较麻烦。空间是那个。但它还是单排的啊，因为它有人做我第一个问题是有人做开的感觉是，就是 three fold 上它做的是之前那个舞蹈学生在做，就他们做那个 three fold， 大家都做，所以我不大熟悉研发我感觉你这里是不是因为某个节目，我看你因为做宽的包是不是为了使得它的那个 multiple fibers 不会太大？你不能有太多multiple fibers， 就是至少把你都要放在要因为你最终考虑什么速度，但是就是之后，所以 VMR 本身不会考虑这个，就是它的那个你经过那些曲线，然后你打到 PTX， 你只是考虑它的 subset 是什么？他们那个vibration 是 smooth 的，那个是看到的。你这个问题也挺做 smooth 的，singular 非常高的 singular 没法定义。其实有的时候嘛， 有人做过 singular，
通过对人体培训，
有人做过 singular 的那个 pattern， 啊，不是 panel，
divisor 系吧？对，之前还有人用过，就是 normal projective variety， 如果它的判定系数是 ample，
那就是 projective，
对，一定是 projective。
对，有人做过这个。
哦，
对，就 singular，但是好像不主流，是不是？大家不太关心。
其实那篇文章还很